Okay, so in section 1.4, proving conjectures using deductive reasoning, we're kind of changing directions a bit here because I've told you in the past that conjectures aren't necessarily true, okay? They're based on the evidence that you see, okay? And now I'm telling you that we're going to prove them, but we're going to change pace a little bit, and we're going to change from inductive reasoning to deductive reasoning, and that's a little different than what we've done up until now, okay? So in the keep in mind section here, it says a conjecture has only been proved only when it has been shown to be true for every case possible, okay? So when you're talking about numbers, that can be really, really difficult because you would have to come up with every single possibility. So in the last lesson, section 1.3, do you remember when we were multiplying two-digit numbers by 11? And as long as that two-digit number didn't add to 10 or more, we were okay. But as soon as we were over 10, we weren't okay. And that was our conjecture. But can you imagine coming up with, well, I guess it wouldn't be that hard to come up with every two-digit possibility because it's not infinite, but you'd have to prove it for every single case possible, okay? And so here it says, in order to prove for every case possible, you do this by creating a proof that involves general cases. Now, sometimes it can be really handy to use the transitive property in deductive reasoning. So according to this property, if two things are equal to the same thing, then they're equal to each other. For example, it says here that if A is equal to B and B is equal to C, then you can deduce that A must be equal to C because they're both equal to the same thing. And sometimes that can be very, very handy using this transitive property. So please remember that one. That might come in handy. And then it says a demonstration using an example is not a proof, okay? So proving has to be general cases, okay? An example only works for that particular case. You can't prove everything using just one example. So let's go over a couple of proofs and let's see if you can figure out how to use deductive reasoning. Okay, so this first example says use deductive reasoning to make a conclusion. Okay, so we're going to make a conclusion from these statements. It says all koalas are marsupials. All marsupials are mammals. All mammals are warm-blooded. And then we know Barney is a koala. Okay, so that's a statement, and we can assume that's true. Barney is a koala because we were told. Okay, so we got to make a statement from what's been said. So often what can be handy is to create a Venn diagram. And let's start with what we were told. Okay, so all koalas are marsupials, all marsupials are mammals, and all mammals are warm-blooded. So if we start with a big circle, and this circle is of mammals. And what do we know about mammals? They're warm-blooded. That's the definition of being a mammal. Okay, so all mammals are warm-blooded. Can we figure out if Barney is warm-blooded? Okay, so all mammals are warm-blooded. All marsupials are mammals. So then within this circle, within the mammal circle, we can include marsupials because we were told that all marsupials are mammals, okay? Koalas are marsupials, so we can stick koalas inside marsupials. Okay, all koalas are marsupials. So if koalas are marsupials, then they have to be mammals because all marsupials are mammals. So if we know that Barney is a koala, we can assume then that Barney is a mammal, and therefore he is what? Warm-blooded. So that's an example of that transitive property. Barney is a koala. Well, koalas are marsupials. Marsupials are mammals. Mammals are warm-blooded. Therefore, Barney has to be warm-blooded. Okay, so that's an example of using deductive reasoning. Okay, so that's just talking about certain characteristics. What about math? Okay, what about using numbers? So it says use deductive reasoning to prove this conjecture. As soon as you see this, We can't use specific numbers. We have to use general cases, okay? And this is where it gets a little confusing. Okay, so it says here, the difference of two perfect squares that are separated by one perfect square is always even. Okay, difference means subtract. So, we're subtracting. The difference of two perfect squares that are separated by one perfect square. Okay, so our first square is going to be x squared. Okay, x stands for anything. Who cares what we throw in there? Okay, because it has to be a general case. We can't use specific numbers. So our first square is going to be x squared. Well, what would be the next square? It would be x plus 1 squared. Okay, for example, if x was 2, then we'd have 2 squared, and we'd have 3 squared. That would be the next one. But it says that are separated by one perfect square. So if we were talking specifics, we'd be talking 2 squared and 4 squared, because they are separated by a perfect square. Okay, so in order for them to be separated by a perfect square, we're going to talk about x plus 2. Okay, one that's 2 digits away from whatever we're talking about. Okay, and so clearly this number here is going to be bigger than this one because it's bigger by 2, and then we're squaring. So when I find the difference, here, let's make this look a little better. When I find the difference of them, the difference is going to be x plus 2 squared minus x squared. Okay, the difference, subtract, of two perfect squares, I'm squaring them, that are separated by one perfect square. That's why I put the plus 2. Okay, is always even. Well, I can't tell until I completely simplify my expression. So remember, this means x plus 2 times x plus 2. X plus 2 squared means x plus 2 times x plus 2, and then subtract x squared. All right, so you got to use your FOIL. We have x squared. We have plus 2x plus 2x plus 4. So this whole thing becomes x squared plus 4x plus 4, but then we're subtracting x squared. Okay? So when I fully simplify this, I have x squared minus x squared. They're gone. They cancel to 0. So I'm left with 4x plus 2. Well, the way that I can tell if something is even is it has to have a factor of 2. That's how we know something's even. It's divisible by 2. So is there any way that I could take this 4x plus 2 and I could express it with a factor of 2? Well, hopefully, if you remember from Math 10, I could pull out a factor of 2. I'm sorry, hold on. This 2 should be a 4. I bet you were already thinking that, weren't you? Where did I get this 2 from? 4, right? This 4 right here. That should be a 4. Okay, so if I pull out a 2 out of each of these terms, I have 2x plus 2. Okay? And because I'm able to pull out this 2, I can now deduce that this is an even number. So that's how I can prove that the difference of two perfect squares that are separated by one perfect square is always even. I make up a general case. Okay, I can stick any numbers in there. When I fully simplify it, I can fully simplify it to have a factor of 2, which makes it even. So that's my proof. Okay, so good luck on section 1.4.